All right, sounds like 10 after to me, or close enough. So let's see if I can see where we are. So you've had section now that talked about Croteau's article? All? Most? All? Okay, so all have been there. Okay, that's good. So Tuesday, and you've looked at this, and so since you've looked at it, and you're not screaming at me, it's possible, or at least some of you have looked at it? Okay, so at least one has looked at it, two have looked at it, and they will not be having problems. I'm going to finish stated preference today and start on techniques, isoquants, and cost. And I'm trying to make it so the week I'm gone, it goes smoothly. One of the days they're going to do the trading game. And so you'll get pieces of paper and it'll be explained. It'll take about an hour and a half. That should be a reasonable amount of fun. And then the second day, Max Offhammer is going to teach you whatever piece of microtheory I'm up to. And so I want to get to a spot where he has a very clean lecture. I don't know what I'm going to do. I don't know where I should stop. But I'm going to forge ahead. And at some point, I want to pick up the Clean Air Act and talk about it for a while. I think you should go look at some of this stuff. You can really choose as you will. This is a rather long New York Times article, New York Times Magazine article, so it's well written, goes a little slow, but it'll give you a sense of what the politics was all about and what sides different people took. This isn't a bad thing to read. The rest of these are important court cases. Blah, blah, blah. That I will put up on the board sometime, today, next time. So that's where we stand. So let's go and pick up the rest of the stated preference. And we're down to... So I think this would be a good place to start. Let's slideshow from current slide. Okay. So how many people took a statistics course, any statistics course? So the idea of a normal distribution is something you've all heard of. Right? This is a standard normal distribution. And what it says is, I happen to know that if I add up all these little pieces up to here, I know that 50% of the values will be 0 or less. So you can imagine it this way. Imagine you had a barrel, and there were balls in the barrel, and each ball had a number on it, and the numbers were centered at 0. So the most frequent number is 0, the average number is 0. And you were to pull a ball out of the barrel at random. And then you could ask, how likely is it that that ball would have written on it a number 0 or less? If you add up all these little pieces, that would be the answer. So the area under this curve up to a point tells you what percent have a number this high or less. You get over here, it's about 66%. It's normal distribution. Around, well, you can actually add this up. 19.1 and 15 is 34, 29, 34, right? 84% are out to here, and so on and so forth. But what I'm going to use this for is I'm going to have a bunch of people. I'm going to make them different by a little bit of randomness. And that's what's going to drive a model in which some people will say, yes, save them wolves, and other people will say, no, let them go. Okay? And what's going to drive it, as I said, is just there's going to be a little bit of randomness. Some people are more wolf lovers than others. And the people who are more wolf loving are the ones who are going to say, yes, save them. The people who are less wolf loving will say, no, let them go. That's what's going on. So let's go through the random utility model, which we just would have said a RUM. And I have simplified this. So if you go back and learn this in an econometrics class, you'll quickly look and say, oh, I see how Peter cheated. So I'm just trying to get the idea across, and I'm not trying to get some of the details right, like whether it's a normal distribution or an extreme value distribution. This is not our problem today. So I have two alternatives. And in each case, each of these two alternatives, people get utility, right? Measure of happiness. So the first, the general formula says your happiness is some constant. A is a constant or a parameter. It's something I don't yet know. I want to know what number A is. That's the objective here. Times the number of wolves. Plus B, another parameter, a number I don't know and want to find, times your income. And that's your happiness. So that's very similar to the one that's on your homework and the one we did before where we had, as you remember, we had two dimensions, one dimension up and down, we had income, the other dimension across, we had wolves, right? And we drew an indifference curve for wolves and other goods, essentially income. So we're in that exact idea. And here I've made the level sets, the linear things. So I've done something simple. Two alternatives. First alternative, the original number of wolves, the original income. The second is the hypothetical. Remember, I go around with my microphone. How much would you be willing to pay for 10 extra wolves? $10, okay? So in that case, that would be $10, and this would be whatever number of wolves I had originally plus 10, because that's the setup. And remember, I can do this again and again, and I can ask somebody else, how much would you be willing to pay to give me a different answer? Right? Or I can be doing this as a referendum. Right? In referendum, I would say, there's 10 additional wolves in this alternative, and would you be willing to pay $10 for them? And she would say, yes. And I come over here, right? I change the number, and would you be willing to pay $100 for them? No. Okay? So by varying P, I'm going to get different answers. Yes and no. Why is that? Well, look at this. So if these people were all the same, there's no difference in the people here, then everyone's getting the same utility before the project, and everyone's getting the same utility from the additional wolves, the way this is written. And people are paying different prices. And so no surprise, as P goes up, utility in the project goes down, and eventually utility here is bigger than utility here, and he says no. So when he says no, he's saying U1 greater than U2, therefore no. When she says yes, she's saying U2 greater than U1, therefore yes. That's our model. So what do? You pick the best. If U2 is greater than U1, then you say yes, I like the project. Now we do a little very trivial algebra, just rearrange it. We know the formulas for U2 and U1, and so when do you say yes? Should I come back and do this? Let's go back one. So we're going to do U2 minus U1, so it'll be A E2 minus E1. Let's see if that's the way we did it. And yes, that's it. A E2 minus E1, and then if you get the last term, it'll be just minus BT. right? Because both have the same income. This income falls out. Doesn't matter what the original income is in the simple model. It's gone. Only what they paid. Well, that's not a great model, because if that's our model, this minus this was 10 wolves. And what will happen is I go to this corner of the room and I say $10. Let's just try and see what happens. So over here, which of you would take my project for $10? Hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many would not? 1, 2, 3, 4, 5, 6. Huh. But look, the model says you're all the same. So how can 10 say yes and 6 say no? Huh. Model not good enough yet, right? It's just not going to work with the data. So I got to find a model that's going to allow roughly, in that case, half and half to say yes and no. Because that's what my actual observations are going to look like. So I need to make the people a little different. And I make them a little different here in a cheaty kind of way. What I do is I say in the project branch, this is that we will do the project branch, some people just like the idea of more wolves more than others. So people with high E's get more utility if the project is done. So now, those of you that said yes, let's see some hands, the ones over here said yes, you're the ones who have big E's. So if you go back to that normal distribution, you're somewhere on the right. You get numbers like a half or 1 or something like that. And then the ones of you who said no, see some no's. No hands. Yeah, okay. So you're the sort of person for whom this is, -1 or something like that. So that will give us the dispersion where some number of you will say yes and some number of you will say no. Because you're a little different. That's what makes it a random utility model. And now I can rewrite my fundamental equation. And when do I get them to say yes? When the value of the wolves times the change in the wolves minus the value of money, utility value of money times the amount of money, plus this little bit of randomness is greater than 0. And since this thing is random, it will be true for some fraction of people. And here's the same thing at the top. And put a different way, those who say yes are all the people who have E's bigger than minus a blah, blah, blah plus D. So as P goes up, what happens to E in order to say yes? It goes up. So the minimum E necessary to go up, right? So here's this thing. So let's say originally the E needed to say yes was here. When E gets bigger, right, then you'll have to have, when P gets bigger, you'll have to have an E way out here. Yeah? Well, it's much more likely to have E's below. Right? Any E below my critical point, I say no. So with a big P, all of those people say no. With a little p, only these people say no. With a tiny p, maybe only those people say no. So as p changes, the percent that are going to say yes changes. So now it should work out. Now I should get a demand curve-like thing. As I crank up p, fewer people say yes. That is, fewer people buy the hypothetical project. And that's what we want. So now how do I estimate this thing? Well, I got 2 parameters, A and B. And presumably I have a bunch of different prices. I had 4 prices in my example last time. And so I have 4 actual data points. A price, $10, percent that said yes from over there, let's call it 50-50. And then if I went to the high number, $50 back in that corner, what percent of you are saying yes? How many yeses do I get? I need at least 1. $40. At some point, one of you would say yes. 1, okay. So at $40, we've got 1 in 10, right? So now I have a bunch of numbers, 10, 20, 30, 40, and I have a bunch of percents, 50, 30, 20, 1. Yeah? And now I fiddle those 2 numbers, A and B, until my model predicts those percentages, just like fitting the line that you had, only a much more complicated version of a fit. Yeah. What is what? B is how much more utility you get for each dollar. A is how much more utility you get for each wolf. Yeah? And I can't measure utility, so you're pushing me on to the next question. The next question is, well, what do I do with this thing? I've now fiddled A and B so that the model matches the proportions that I have observed. But what do I want to know? I want to know what's a wolf worth. So if I had 1 more wolf, utility would increase by A, right? If I had 1 more dollar, utility would increase by B. And so if I wanted to keep utility the same, so looking at 2 points on an indifference curve, 1 wolf up and A over B dollars down keeps utility the same, or 1 wolf is worth A over B dollars. So the thing ultimately spits out the value of a wolf in terms of the ratio of the 2 coefficients. That's a random utility model. And that is our workhorse model for all things in which you say yes, no. So any dichotomous choice. Some people went to work and some did not. Same model. Some people, a bigger version of same model. Some people took BART, some people took the bus, some people took their bicycle, and some people walked. All fractions. Again, just a blown up version of that model. So that's a real workhorse model for us. And it's due to, the way we use it here is due to Dan McFadden, a Nobel laureate from Berkeley. And originally it was used for BART. Okay, so now we know about random utility models, and that makes you advanced economists. You no longer claim that you've just taken the basics. You're now all advanced. Another way to do business that melds 2 things we saw. One thing we saw is we saw this idea of hedonic regression. We take the value of a house and we explain it by its characteristics, how many square feet, how many bathrooms, etc. And in our case, being environmentalists, how many coliform bacteria we had in the nearest body of water. Right? And we take the other idea, stated preference, and we put them together. So instead of just asking about a project, we ask about, here you go. Instead of just asking about a project, we ask about variance on a project. And the easiest one to understand I found was a set of gardens. So really there were a set of flashcards that showed, if I remember right, 3 different gardens, depending upon how much native plants they had in. Why would you currently care about native plant gardens? A little bit of environmental history time. What? Water use. What did this area look like before the Spanish got here? What did this place look like? What? So, yeah, and what's in between the trees? What grass? What grass? Is it the European grass? No, because it has the word European in it. That's a good clue. Yeah. So it's the bunch grasses. These are really different things. So if you have a bunch grass has roots that go down 25, 30 feet. Right? So the bunch grasses would still be a little bit green out there. They wouldn't be all dry like the European grasses are. Those are shallow root grasses. And it's introducing the cattle that favors the European grass. This is a whole wonderful piece of ecology about what happens when you bring the cattle and how tightly the range animal and the grass are coupled. And they are. The cattle are heavy, and they create a bit of a hard pan beneath the soil. And so the bunch grasses can't get through it. If you want to restore them, which people are doing in Marin, what you do is you get a plow that's about this wide, but about 6 feet deep. And every 3, 4, every 6, 8, 10 feet, something like that, you rip all the way through the hard pan. And then you plant back the native grasses, and they send their roots through the hole you made. And then they widen out the hole and break it up. And of course, if you put cattle back on it, then you have to keep doing that. And if you do something else with it, then you don't. So it's a very different world. At any rate, the point of native gardens in a place like this is that the amount of water you would put on a native garden in California, in this part of California, probably be 0. Right? It would survive nicely. You do not have to water your bunch grasses in the summer. They'll still look okay. So that's a very different type of garden. That's why we care. So we show you a picture. Here's a garden with 100% native plants. Here's a picture with 30% native plants. Here's a garden with no native plants. And they have attributes. Clearly, the water use in the native plant garden is way down, and that's the advantage of the thing. But getting them going has some cost, and they don't have an intense color display. So if you were properly southern, do we have any southerners? Do people have gardens? Yeah, it's just an attribute of the South. That it would be better to have a pretty garden than a giant mansion. Yeah. Right, okay, so it's all about your garden. That's how you're going to be judged. It's real simple. If you have a California native plants garden, you're going to get what? 0, right? It's like, what are these northerners? Something weird came into our neighborhood. Yeah. So people do have desires for attributes of the gardens other than it fits properly with the California ecology and we don't really have the water to go splash on this. So we show them cards of what the garden actually looks like. And here's roughly what's on the cards. No natives, intense color, low cost, high water. This, I guess, is 20%. We still keep the color. But we change these two for this particular garden. And then all native as well. It's dull. I'm sorry. But it's low cost and low water. And we say pick one. So how does this work? Again, this idea of a random utility model. Here I've just written down the deterministic part. Utility is a function of color, cost, and water. We're the 3 alternatives. And utility depends upon the quantity of the attributes, right? The color, the cost, and the water. And again, I can vary things. So I have the natural variation in the cards. I can also fool with the cost to create more alternatives. Then I find out what percent would say yes, right, to each card with different costs on them. And then based upon matching my model prediction with the reality of who said yes, I figure out what A, B, and C are. And now, look, I have figured out a hedonic. I actually now know the value of all these things. And as usual, I can take the ratio of A to B for the money measure of color or the money measure of water. And I can find out what each of the alternatives are worth. The value of this over a simple, would you buy the native garden, yes, no, is now I learn what it is that makes somebody want a garden. So if what they want, if they pay a lot for color, then I go back to my friends who breed plants and I say to them, I could get them into the native gardens if you could hunt around a bit and for not too much water or money cost, find me a way to get more color in there. So as a practical matter, if you're trying to sell native low-cost gardens and you found out not just that people prefer the non-native gardens, but you found out why they prefer the color, then you have a way to engineer a product that they might buy. And that's, of course, something you'd like to do, right? You'd like to go out there and use your skills to re-engineer native gardens and save 30% of the water in probably more than that. Yeah, way more than that. 60, 70% of all the water in urban California. Not the industrial stuff, but just the municipal stuff. Probably all goes outside. That's probably about right. So you could have a really big impact. And that would be what you'd have your economist friend do for you. You'd say, hey, find out for me what attributes they're willing to pay for. Okay, well, let's wrap this piece up. So the idea of stated preference among economists was always considered to be inferior to revealed preference because of this possibility of lying. And that was always just kind of an academic debate. And then the Exxon Valdez came and spilled the oil in Prince Rupert Sound. And suddenly, the state of Alaska was asking Exxon to not just clean it up, but to pay for the natural resource damages. And they wanted not only the active damages, what did they do to fishing? They wanted the passive use damages too. And they went and found the people who were best able to estimate that. My former student, Richard Carson, and my colleague, Michael Hahnemann, both of whom I would say are the world's experts in how you estimate passive use damages. The rest of the economics profession lined up with Exxon, and they were paid well for it. Do not feel sorry for them. And so the people who wanted the